All right, so let's get started here. And what we're going over is actually the 2013 question one of part two. It's a 10-point question. All right, I've written it in terms of a worksheet, so you have some space in between, but it's actually an entire AP question. So let's get going. All right, so let's read the question, see what kind of good little juicy details it's giving me. A student prepares a 100 milliliter of a saturated solution. This is screaming to me equilibrium. Okay, solution saturated is equilibrium. That means that the solution cannot hold any more ions, and any more extra ions would come out of solution, and that's what solution equilibrium is. Okay, so we're adding 0.50 grams of magnesium fluoride to 100 milliliters of distilled solution, stirring until no more solid dissolves. Assume the volume of the undissolved MgF2 is negligibly small. A saturated solution at equilibrium is analyzed and determined that the fluoride ion concentration is 2.4 times 10 to the negative 3. So, number one, let's write the chemical equation for the dissolving of solid MgF2 in water. So none of this really helps me for this question. It's an ionization reaction. So I take my MgF2, all right, and it's a net ion reaction, but essentially it's a solid, breaking apart into Mg plus 2. And it does not do this. People love to do this, and I'm not sure why. Okay, this is a magnesium plus 2 ion and 2 fluoride ions that are basically in a crystal lattice of some three-dimensional shape. Okay, so do not do that. Okay, so it's 2 fluoride ions, 2F negative. This is aqueous. Do you need the states of matter? Probably. I would say it's a good idea to show off and show that you know that. I'd write double arrow because it's at a saturated solution. Okay, that's all there is to it. And you get a point just for that. All right, so aye, Captain, here we go. Calculate the number of moles of MgF2 that dissolved. All right, well, they're telling me, party people, that I have a saturated solution at equilibrium, okay, and that there is that much, okay, that much molarity in terms of F negative. So the concentration of the F negative is 2.4 times 10 to the negative 3. So as we've done before, molarity is equal to moles over liter. So all I have to do is multiply moles times liter and I solve for the number of moles. Okay, sort of. There's some stoichiometry involved. All right, so they want to know exactly how much of this compound dissolved. And it's a funny question because this is not a molecule, it's a formula of a crystal. So they want to know how many moles of this formula of a crystal dissolved. Careful, there's 2 F's per one of these formulas. So let's go find the moles of F2. Well, I have the molarity. Okay, so I take my molarity, 2.4 times 10 to the negative 3. We're not afraid of small numbers. And I'm going to multiply that, okay, times my liters. Okay, what's the liter? Well, there's a what? Well, if it's a, this is per liter. Now I should really put moles over liters here. And this is something we should know already. We've been doing this a lot in acid and bases, okay, or we've done this in solution type of problems, and we're going to times this by the liters, okay, and there is, because there's 100 milliliters, that of course is 0.100 liter. We should have that conversion, okay, and certainly that will give me my moles, all right, and if you do that, you can get your moles there, all right. And what you get, of course, is 2.4 times 10 to the negative 3. And that, of course, is the moles. Now, moles of what? That's actually the moles of the fluoride ion. That's not this. And what do we know? We know that there are, look at that little subscript, 2 fluoride ions per one what? per 1 formula, MgF2. So I'm going to do that and divide by 2. And again, the reason for that, a little bit of stoichiometry leaks into our problems. They want to make sure you're aware of those ratios. So essentially I'm dividing by 2, and the answer, of course, is just real quickly 1.2 times 10 to the negative 3. You should be able to take and understand if I divide this by 2, I'm just dividing this number by 2. Okay, and you just maintain that if you're doing a multiple choice kind of problem. And of course that's of course equal to the concentration of the magnesium fluoride that dissolved. All right, now of course you could write this all in one step, okay, and they show you how to do that certainly in the AP key. I'm just making all my students aware that moles times the liter, the molarity times the liter gives me my moles, and then I needed to do some stoichiometry. Obviously we can do this in one full step, all right, but again, teaching it step by step so you can recognize the fact. And again, in this question they actually give you a point for converting to moles, and then I'll give you another point for noticing that there is a stoichiometric value that you have to recognize. Obviously, if you miss this, you missed the point, and then when you use that for the next part, there'd be no double jeopardy. All right, but clearly, points to be had here. Look, it's a 10-point question, and honestly, you should have 3 points already. Now, if you missed a stoichiometry, that's on you, because again, it's all about practice. You've got to look at the ratios. They're going to make you want to look there, so you need to look there. Let's go on. Let's go on to number III, Captain. Determine the value of the solubility product. Fancy word for KSP. So what do we know? Well, if we look at our reaction, the KSP is going to be, now it's products over reactants, coefficients become exponents, solids and liquids do not apply. So KSP or KQ, KA, KB as we're going to see is equal to the same thing. So I take my Mg plus 2 and I'm going to multiply it by the concentration of my product, other ion, and notice I make it a square. Why do I make it a square? Because there's a coefficients become exponents, and I do not put this under this guy because solids and liquids do not apply. So that's my KSP. And again, as you do KSPs, you're going to always recognize it's just the what? The product of the ions. So they want the value of the KSP. Well, because in the problem they said we have these concentrations in a saturated solution, that of course means at equilibrium. I can't say that enough. So those are the values at equilibrium. Now, if you don't see that and you want to write a nice table, you can. You don't need to in these cases. Of course, we have 0, and we put the salt Mg fluoride solid in the water. We're not going to need, we're going to assume it's all solid state. When we do equilibrium problems, assume it's all the way 100% into this. Now, of course, it's going to go forward. So this is plus x, and this is plus what? 2x, yes. And of course, you add that, that'll be x plus 0. 2x plus 0 is 2x. Now, we didn't need to do that because we already know the concentration of the F. And what is that concentration? They already gave it to us as 2.4 times 10 to the negative 3. And that's plus 0. And then of course we indirectly got the Mg. Mg is going to be half that, right? So it's got 1.2 times 10 to the negative 3 is the Mg fluoride, or the Mg. Notice there's 1 magnesium per 1 MgF2. Now, of course, plus 0, it's the same number. So you didn't have to do this part. You can recognize that that was the value. So when you plug this in, party people, we got Mg plus 2 is basically going to be 1.2 times 10 to the negative 3 times 2.4 times 10 to the negative 3, and you can't forget to square this. Okay, so essentially you square this number, times it by this, put this in your handy dandy calculator, and you get a value for the KSP, which is an equilibrium constant, which is, notice they gave you the temperature, it's temperature specific, and you should get 6.9 times 10 to the negative 9. There's no unit for equilibrium constants, dimensionless number. And this is a 3-point question, okay? They're going to give you a point for the correct value of the magnesium, which has to be 1/2, because this wasn't 2x and this is x. Okay, so maybe that would have helped you, but knowing the stoichiometry, this is 2 to 1, I think you could have worked yourself out there. So they're going to give you a point for another stoichiometry relationship, okay? They're going to give you a point for the correct setup, and then for the correct value. So my gosh, this is 1, 2, 3 points. This one is 1, 2, and this is 1. So think with me. The goal here for a 10-point question is at least 7 out of 10. 70% of this test gives you a 5. So 1, 2, 3, 4, 5, 6. You should really be cashing in right here. This is 6 out of 10. So if we haven't gotten to any kind of crazy questions yet. So 6 out of 10 is already earned. And I'll tell you right now, traditionally students do not like KSP. But come on, that's free points. So now we're going to move on to see if we can get at least one more point. Obviously, we're going to get all 10, hopefully, if I know what I'm doing. All right. So the next question is now letter B. And essentially what we're going to do here is it contains 500 milliliters of a solution in which calcium and barium are present at a concentration of 0.1 at 25. Notice they're giving you the same temperature. Okay, they have to let you know that the KSPs are staying constant. Again, if you don't know what you're doing, draw yourself a container. So we've got a beaker. It has 500 milliliters. We have calcium plus 2. And we have barium plus 2. They're present at a concentration of 0.1. All right, so they're both at a concentration of 0.10 molar. Student intends to separate the ions by adding sodium fluoride. So we're going to add sodium fluoride. Now we know sodium fluoride is soluble. Group 1 ions and halogens mean that these are not going to dissociate very well because they have low charges. Coulomb's law. Water can break them apart. So we're going to add 1 drop at a time. So 1 drop of Jupiter. So 1 drop at a time is being added to this solution. What are we really adding? Well, we're adding sodium ions, which that's not going to really matter here because there's no sodium ions involved, so that's a spectator. But we're going to be really adding a common ion, which is F negative. So we're increasing the F negative concentration. And what are they giving me? They're giving me the KSP for calcium fluoride to be 3.5 times 10 to the negative 11, because the calcium is pretty insoluble. Look at that KSP. And then they're going to give me a KSP of barium fluoride, and it's equal to 1.8 times 10 to the negative 6. Now, I don't want you to be robots. I know we've done a question just like this, and you might want to attack it exactly the same way, but you don't have to. And here's my reasoning. Both of these ions are the same concentration. Notice also, party people, they both have the same formula. Okay, these are not molecules. There's 1 to 2. So the same stoichiometric ratio, same concentration. So that being said, all I can do is look at the same KSPs. All right, so here's calcium fluoride, and its KSP is 3.5 times 10 to the negative 11. That's calcium fluoride. And let's look at another one, and that's barium fluoride. These are my YouTube diagrams. And so the question is, when it's saturated or present, okay, we're probably in a scenario where we don't have enough fluoride on. So right now, my Q's for both of these are in front, okay? And the question is, as I add fluoride ions, to which both have, the product of these dissociation reaction or ionization reaction, remember it's products over reactants, coefficients become exponents, and solids and liquids don't apply. So the point is, my product value is going to go up as I add fluoride ions. So what's going to happen is my Q eventually is going to have to equal K, and then it's going to pass over to the dark side, which is going to make the reaction go where? In reverse. And that's going to cause what? Crystallization or precipitation. So which will precipitate first? Well, looking at the KSPs, and I only have to look at the KSPs in this problem because everything else is the same. The concentrations are the same and the formulas of the salts are the same. If the formulas were different, if you think about it, the KSPs would give me what? Someone would be a squared and somebody wouldn't. Okay, just like the other problem. And if the concentrations were different for the other ion, I'd have to do the math to find how much fluoride, okay, would have to be made. This case I don't. So I'm just looking at the KSPs. Now who's got the smallest KSP? Ah, right there. So what does that mean? That means that the equilibrium position is farther favoring the reactants, which means when Q equals K is going to be a smaller amount of F I have to add. So as I add F and this Q becomes bigger, it's going to equal K before this one, and therefore it's going to what? Go forward beyond that. And once it goes beyond that, we know that the reverse reaction, now moving toward equilibrium, this is KSP right here. So we would say, very simply, that this salt, okay, calcium fluoride, because of its smaller KSP or KQ, it's the same one, all right, would precipitate first, all right, because its KSP is smaller. Thus, the ion concentration product will be the first to exceed KSP. Many ways to say that, but its KSP is smaller and you have to justify it. Therefore, by adding fluoride ions, its Q is going to exceed its KSP before the other, and therefore it'll be non-spontaneous in reverse before the other. So when we add the same amount, we might be in a scenario where we're now here, but this one now is still here because this equilibrium is so big, its position is favoring the products more. Okay, so that explains B, and believe it or not, that's a 1-point question. So if you were stuck on this question and spending 10 minutes out of your 20 minutes that are basically designed for this question, okay, you should just skip it, okay, or go back to it if you have time. But if you spent, and I say in these part 2 questions, questions 1, 2, and 3, if you spend more than 20 minutes, you're starting to encroach on other questions you could be spending time on. It is an absolute shame to spend times on questions that you don't know and never get to the questions you know. Strategy is very important, but like I keep saying, there's an easy answer to all of this. So again, if you got lost in the sauce, give it up. This is a 1-point question. If you still got 6 out of 7 at this point, you're doing great. All right, so let's move on to C. Or better yet, let's go in order and go on with BII, Captain. So onward we go with part BII and BIII, Captain. So with IIB, calculate the minimum concentration of F negative necessary to initiate the precipitation of the salt selected in part I. BI. So we said previously, okay, that calcium fluoride is going to be the salt that precipitates first because it has the smallest K. That means its K position is closer to more reactants, so need a lot less of them in order to have a Q equal K and then go beyond it to go in the reverse. It's all the same stuff here. So party people, what's our KSP here? 3.5 times 10 to the negative 11. So 3.5 times 10 to the negative 11 is my KSP for calcium fluoride. Okay, so that's my calcium fluoride. Now, they want the minimum concentration of fluoride necessary to initiate the precipitation. So the KSP is equal to the calcium ion times the fluoride ion. However, there's 2 here, so that's a coefficient of 2 because the reaction, of course, becomes calcium plus 2 and 2 fluoride ions. So party people, that's what happens. That's how we get that coefficient of 2. Okay, now what do we know? They want the minimum concentration. All right, well, how much calcium plus 2 did we have in the beaker? We had 0.10. They told us that right here. Temperature didn't change. So they want to know, all right, the minimum amount of F2 to initiate precipitation. Okay, all right, well, we can calculate that because this will be our X, and we have this to be, again, my short-term memory is gone at this height, is 0.10. So we plug this in, and we get 0.10 molar times our X, not 2X, or X, whatever this is. We're trying to solve for this, okay? And of course, it's squared, all right? And of course, we're going to do our math. This number equals this times X squared, all right? And so if you want to see what this means, I'm timesing 0.1 times 3.5 times 10 to the negative 2. When we do that, what you're going to do is you're going to multiply that by 0.1. That makes this number smaller, so it becomes 3.5 times 10 to the negative 12. And of course, that's not what you do, Bad Grodzki. What we're going to do is, we're going to take this negative 11 here, and then we're going to divide by 0.10. And of course, that's going to equal X squared. And of course, when you do that, that's going to get bigger. So that becomes 3.5 times 10 to the negative 10. It got bigger. And that equals X squared. And then, of course, we're going to take the square root of both sides. And then X equals, okay, using your handy dandy calculator, 1.9 times 10 to the negative 5. And that's a molarity. That's what we found here. Okay, and that's the answer in terms of the fluoride ion. So very simple, okay? We've seen this before. We definitely have. You have to be able to try to identify and unpeel the onion, so to speak. So in III, they want the least amount of volume of the initial added fluoride ions from sodium fluoride that must be added to, now I forgot to keep going on this, to an III, I should say, to initiate the precipitation of the selected salt. So how much of this do I have to add to a beaker that already has calcium ions and barium ions to initiate the precipitation of the first salt? Well, we recognize that calcium plus 2 is going to be the salt that precipitates first. So what they want to know is, well, how much of this do I have to add to precipitate this? Well, we just found something very important. We found that we have to have a molarity of 1.9 times 10 to the negative 5 molar solution. Okay, that's the molarity. And we added enough fluoride ions. Remember, NaF breaks apart to Na plus and F negative. This is a spectator, so we really consider only the fluoride ion, which is a common factor for both. And what we know is this is the concentration that we need so that calcium can its Q can equal K for reasons we just explained. And that precipitates first because of a smaller KSP. Now, what we're going to do with this number, this is the molarity in a total of 500 milliliters. Now you say, well, how do I know that? Because in the beginning of this problem, which actually started on this page here, we've got a beaker that contains a solution of both at 500 milliliters. We added some sodium fluoride, which doesn't add to the volume. Okay, we're just keeping things straightforward and easy. So we have a molarity and a volume, which would give me the total moles added. So I could actually take this number, times it by 0.50 liters, because I know that molarity times volume would give me moles. And then I would take that mole, okay, and solve for the volume I'd have to have, all right, if the molarity of my initial compound was 0.2, right? So that's all I'm doing here. I can just solve for my moles, molarity times volume if that's in liters, get my mole here, and then knowing that the initial concentration of this is 0.20, I can solve for it. Or I can use my dilution formula, which is MV equals MV. Either way, that's what we're doing here. So if you want to use the MV, take your 0.50 liters, take the molarity, which is 1.9 times 10 to the negative 5, which is what the fluoride ion concentration must be in order for precipitation to first occur. We want to solve for this volume of 0.20 initial molar. So really what we're doing is solving for the moles and dividing by the molarity to get the new volume. How much of this 0.2 molar solution do we need to achieve this molarity? That's it. So when you set that up, and you could have done it two different ways, okay, what we get is the volume is equal to 0.047 liters, or I'm sorry, 0.0047 liters, which of course is going to be about 4.7 milliliters. Either way, you can answer it any way you'd like. Okay, so that's what that's about. So all you're doing is going to do that math, and you get a volume that's pretty darn small. Now, why is it small? Oops. Why is it small? It's small because the concentration of your F is tiny. You don't need a lot of this very concentrated NaF solution as compared to how much you need. Only a little bit of F is going to come out or be able to go there. Remember, the KSPs is so tiny, all right? So you only need a small volume of a pretty darn concentrated solution when compared to this value. So that's why it's only 4.7 milliliters, okay? And that should make sense to you. All right, last little piece, all right? And again, I wouldn't get down on any of these questions because let's say you didn't even see this question. I really think that you should be able to pull this one out. But if you didn't see this one, you got lost in the sauce a little bit, okay? This is only what? 1 point, all right? So that was only a 1 point question. So don't get crazy. Last little piece, there are several ways to dissolve salts that have limited solubility. Well, we know when we measure salts that have KSPs, they always have limited solubility. So describe one procedure to redissolve the precipitate. So if I want to take something like calcium fluoride or barium fluoride that barely dissolve, okay, they barely become free ions because, well, Coulomb's law states that the high what? Charges and the small sizes that they have by losing electrons, okay, make this lattice energy so high that water can't break apart, something we've learned. But how can I make them? They don't like to dissolve. Well, what do we know? Solubility is a component of temperature. If I make the solvent have a higher temperature, it could dissolve more. Okay, and of course temperature changes the equilibrium constant, KSP. Also, couldn't I add more water? Right, so the two major factors in solubility is how much solvent and what the temperature of that solvent is. Anybody who's ever made rock candy, it's two what? It's basically 2 cups of sucrose or sugar, table sugar, to 1 cup water. How in the world do you dissolve 2 cups of sucrose and 1 cup of water? Higher temperature. Make the solvent move faster. It's able to interact more with this solute particle. But ultimately, you can add a lot more water. And theoretically, all these guys can completely dissolve if we add tremendous amounts of water to them. Right? Because if you increase the amount of water, remember molarity is what? Moles over liter. Okay, if you add a lot of water to the solution, the liter of solution is going to increase. The molarity is going to what? Decrease. If the molarity decreases enough, hello, so that the Q is now what? Less than K. We've been through this, right? You can actually go in the forward direction and dissolve. So again, many other possibilities probably, but increasing the temperature of a solvent helps in dissolving. Adding more water, of course, that's going to really affect and make Q smaller than K. All right. So hopefully you got 7 out of 10, 6 out of 10. That's a good place, but I'm sure the one you got wrong, you're going to kick yourself, but not too hard. Okay. Again, it's practice. And the more you practice, the more you're going to see these problems. All right. Hope that helped.